Hello, good evening. It's our easy lecture series. Today is May 25th. It is 7:12 p.m. My time. I'm in Switzerland, Zurich. And today with me are Dr. Han Yang, who's going to talk about energy dissipation by viscous damping. And Mr. Heshan Wang is also here. And we will continue this over next few lectures as well. But right now, Han, please. Yes, your time is what? Your time is noon.
10 a.m.
No, 10. I'm sorry, 10:15 a.m. Yes,
10:15, yeah.
It's 9 hour
Yep.
difference. Okay. Okay, please, Han, go ahead and let's talk about viscous damping.
Okay.
Share
Yep.
your screen.
Let me just share my screen. Here it is, full screen, and okay.
Good.
Can you see this?
Yes, perfect.
All right. Okay. So today we're going to continue our lecture on the modeling of energy dissipation in earthquake solute structure interaction. Today we're going to continue to talk about theory and formulation. Specifically, we will be talking about energy dissipation due to viscous damping. So we will always start from the same the same place, which is the energy balance in a dynamic inelastic system. We have the equation of motion in its global incremental form, like this equation shown right here. Later, we will actually come back to this equation when we talk about the actual formulation to calculate the energy dissipation due to viscous damping. And then from the equation of motion, we can derive the energy balance equation in its global rate form. And this is the equation. And from this equation, we can identify all the energy terms, the kinetic energy, and also this is our topic today, the energy dissipation due to viscous damping, and then everything else that's happening inside the material. So viscous damping, physically, it is comes from a dissipative interreactions between the solids and the viscous fluids that exist in a solute structure interaction system. You can imagine for the structural part that's above the ground surface, whenever you have some kind of motion or vibration, there's going to be interaction between the structure and the surrounding air, and the air is a type of viscous fluid, and that is a dissipative interaction. And also in soil, you can have saturated or partially saturated soil that also serves as kind of a multi-phase media that has a dissipative interaction between the solid and the viscous fluids, like waters and stuff. This is a very important source of energy dissipation in a solute structure interaction system. So here, there is a movie that I found actually on YouTube that shows just a very simple example that shows the vibration of a cantilever beam because of the surrounding air. You can see the the amplitude of the vibration actually goes down when you have more cycles of vibration. As you can see at the beginning of the video, the cantilever is pushed all the way to the bottom of the screen. When you release, that's the amplitude of your vibration, but then quickly it goes down to almost like just one, like a fraction of the original amplitude. Yes, please.
So essentially it's going to go down to zero. Essentially it's going to vibrate and stop and slowly stop, and this is all because of the beam vibrates in air, and there is air going around, and there's a wind and so on, and vortices, and so it's going to slowly slow down. So we're actually going to try to we're going to make a model like this, and we're going to show this next time. Well, not next time, but after numerical damping. This is going to be very interesting. Yes, go ahead. Thank you.
Right. Okay. So this is just a simple example, and as you can imagine, the similar process will happen on a much larger scale in a solute structure interaction system. So in terms of the modeling of viscous damping, we usually use so-called Rayleigh damping, or its more general form, the Kohei damping. So a couple of important features on those two types of damping that we use to model viscous damping is that they are linear, they are velocity proportional. The second point is that they are explicit in terms of the damping force. Later, when we show the equation, you will see that the damping force is directly a function of the velocity specific locations, and also there is a damping matrix, and there are ways to calculate the damping matrix, and also reasonably choice of the damping parameters. So because it's explicit, so it has a relatively low computational cost, and also can be used to target a specific frequency range of motion, and it has a large damping ratio for high frequency motions. So this plot I'm showing on the right side here, you can see is a plot of the damping ratio in terms of specific frequency of motion versus the frequency of the motion. So as you can see, this thick black line is the overall damping ratio, and it is a combination of a mass proportional term and the stiffness proportional term. So as you can see, as the frequency increases, the mass proportional term decreases to all the way to almost zero, and then the stiffness proportional term increases actually linearly. The combination of them gives you a curve like this. So this is like a damping ratio. But later we'll go back to this when we talk about how to choose the damping parameters. So the damping parameters need to be chosen very carefully. So just because of the following reasons. Now, the first one is that we want to achieve an almost constant level of damping ratio for intended frequency range. So just by looking at this plot, you can see if we are close to this, this value of the curve right here, we can achieve an almost constant damping ratio for this part of the curve. But outside this region, the damping ratios are actually very high. So we need to choose damping parameters reasonably so that the curve can cover your intended frequency range, and then within that range, the damping ratio is almost constant. And if we don't choose the parameters reasonably, then a couple bad things can happen. So the first one that has been observed is that there's going to be unrealistically high damping forces, especially outside the range that you choose. If you, like, for example, if you have bad choice of damping parameters and you're outside the range, then you can see that the damping forces are really, really high. And that also leads to another issue that's directly related to energy dissipation. That is, sometimes really damping is observed to overshadow the plastic energy dissipation, which is a topic we have been talking about in the past few lectures. That in that case, there are multiple energy dissipation mechanisms that they're all physical energy dissipation mechanisms that should be modeled reasonably. But when you have a overpowering or unrealistically high Rayleigh damping that actually overshadows the plastic energy dissipation, and that makes your overall analysis unrealistic.
Can I say something?
Yes, please.
So you mentioned something, and we're going to go back to this when you show equations, I guess, in the next few slides. Viscous damping is velocity proportional.
Yes.
The faster your solids, your structures move, the more damping you have. Plasticity damping is, material damping is displacement proportional, because, you know, with more displacements, you get more strain, so you get more plasticity, so you dissipate more energy. But this is what the last point here, that overshadowing plastic. Sometimes, a lot of times, viscous damping is used to actually model energy dissipation by plastification. For finite element programs that they don't have plasticity or inelastic material behavior, they will put viscous damping and make a trick that say that this is a dissipation. It's not true. It's a trick that you can use every once in a while, a little bit, for this one range of frequencies. But again, remember, it's a frequency dependent, it's a velocity dependent damping, and it is not to be used for displacement proportion, just like what you said. So go ahead, please.
Yeah, right. Okay. So that's the general some general points for the modeling of viscous damping. And here are the actual equations that we use. So again, we start from the equation of motion. This is the same equation we have shown earlier when we talk about the global energy balance for a dynamic inelastic system. So we can see the three terms on the left-hand side. So we have the, this is the acceleration proportional term. This is just acceleration multiplied with the mass matrix. And then the second term is our topic today, which is the viscous damping term. So here, this is the viscous damping matrix multiplied with the velocity vector, and the multiplication of this term is basically the damping force. Okay, and then we have the material part. We have the elastoplastic stiffness matrix multiplied with the displacement vector. So as Professor Bohr just mentioned, so this is the why we say that the plastic energy dissipation is proportional to displacement because of this term, and all of them add up to, of course, the external loading. So the second term is the dumping, is the viscous dumping term. So here we have the viscous dumping matrix, and as we mentioned before, we usually use the so-called Rayleigh damping, and this is the expression for the viscous dumping matrix of the Rayleigh type. So here we have the viscous dumping matrix Cij equals to a combination, a specific combination of the mass matrix and the actually this is the elastic stiffness, and we have the damping coefficients, and I have mentioned before we need to choose them very carefully to achieve a desired level of viscous damping but not overpowering. Okay, and once we have the expression for the Rayleigh damping, the actual calculation of energy dissipation is rather simple because it's simply just the force, which is this first two term, basically the damping matrix multiplied with the velocity vector. That gives you the damping force, and then multiplied with the increment of displacement that gives you the energy dissipation due to viscous damping during a certain increment of loading. So coming back just a little bit on the choosing of the damping coefficients, because it is a very important topic that has been talked actually not nearly enough, I feel like, but we should be really careful. Right. So here is a very practical procedure given by Professor Hall in his paper in 2006, which is actually very useful that we have been using in the past few years. So here are the several steps. So first, we want to select a desired amount of damping and a frequency range that we want to cover by this specific type of Rayleigh damping. So here, this is a plot. This is the same plot we have shown before, but with more notations. So as you can see, this is the damping ratio as a function of the frequency. Here is omega, but it's practically the same as the frequency f. Yeah. So here, let's say we want to cover this frequency range from omega hat. This is the starting of the frequency range. This is the tail. This is the end of our range. So from omega to r times omega hat. So basically those two parameters, omega hat and this r, defines a frequency range that you want to cover. And then we also want to select a desired amount of damping. Let's say in this case, we use the parameter Kc to represent this desired amount of damping. So once we have selected those two physical properties, now we can compute a upper and lower limits of the damping ratio. So this is given by this equation. So delta basically gives you a range of the damping ratio that are within the specific range that you have chosen. So the maximum amount of damping is sigma plus delta, and the minimum amount of damping ratio equals to the sigma minus delta. So as you can see, this is the range. So now, once we have calculated this range of damping ratio, we can see if these bounds are satisfactorily narrow, because sometimes they are not, and if they're not, you have to re-choose your range. Okay, so if they are narrow enough, then the damping coefficients can be calculated using these two equations, and then we get our AM and AK, and these are the two coefficients we have shown earlier. So using this procedure, you can have a pretty much reasonable choice for those damping coefficients. So just coming back to this equation, after you got this AM and AK, you can use that in your simulation, and also you can use that to calculate your damping matrix, and then use from there, you can calculate the energy dissipation. And again, this is the equation we use to calculate energy dissipation at each increments.
So can I just go back? I'm sorry,
Yes.
go back. So just to note, so this Rayleigh damping is probably the most widely used damping, but the one you mentioned at the beginning, Cauchy damping, is a more general case of Rayleigh damping. So Rayleigh damping is Cauchy damping of order 2. Cauchy damping can be
Right.
higher order, 3rd, 4th, and so on. So Cauchy damping can cover more frequencies, but it, I mean, it's more complicated. One of the big reasons it complicates computations because it does fill up the damping matrix. Because remember, for the Rayleigh damping, the shape of the damping matrix is the same as the shape of mass and stiffness, because you're adding up essentially
Right.
alpha m times mass matrix plus alpha or AK times stiffness. For Cauchy damping, or order higher than 2, 3, 4, and so on, it's going to grow. The actual damping matrix gets thick. The bandwidth is much higher. So usually it's not used, but for some smaller problems it can actually be very useful. Yes, go ahead.
Yeah, that's right. And I just remember another thing we can probably discuss here is that if we look at the tails, like when you go to higher frequencies, the damping ratio for Rayleigh damping is going up. This
Yeah.
is like it has to go, like no matter what the choice of the coefficients is, it always goes up. And in most cases, I think this is actually desirable, because in finite element simulation, we introduce like unreal, like artificial high frequency motions, like because of the discretization of the system. So sometimes this is desirable, but again, you have to be really careful when you use this kind of stuff.
But you have to be careful. If you really want to model high frequencies, you need to know that this is
Right.
happening. You're actually over damping high frequencies, and we'll go back to this when we talk about numerical damping. And then also the lower frequencies,
Yes.
you are essentially over damping those too.
That's right.
Yeah.
Yep.
Okay. Yeah. Go ahead.
So that's it for the basically for the calculation of energy dissipation due to viscous damping. And here are the references we used,
Good.
and that's some of my collaborators, funding sources, and again, all of this information, they are other calculation is implemented in the Real ESSI simulator. So if you're interested, please go to the website of Real ESSI simulator and try it out for yourself. And later we're gonna actually talk about some examples to illustrate all these calculations and stuff.
Yeah. So we'll make some examples and illustrate all these previous steps. Thank you very much. So with this, we'll stop our recording and we'll see you next time, which is going to be a few days from now. Thank you.